To one of our talks before? Well, that's interesting. Who has been to one of our talks before? Okay, all right. All right, so this is, Simon's going to do the formal introductions in a second, but just briefly, this is going to be an experiment for a couple of reasons. One is it's Burkhard and I talking together, which is, think of your two favorite foods which don't mix, and that's what it's going to be. But the other thing is it's being recorded for radio. So this is going to work a treat. But a couple of things I'm going to try. One thing, so there's a couple of things, as you know, are in every talk. And so I'd like you to yell out when we do it. Okay. So if I say, what is 0.999 ... The answer is? 1. Yell it! 1! Good, okay, all right. And you all know Krusty the Crown, right? Yes. Who's in charge of maths education in Australia?
Krusty the Crown.
Yell it!
Krusty the Crown.
Yell it!
Krusty the Crown.
That's better. How do you expect to stop a war if you don't yell out? All right, okay, all right. Thanks, all right, we'll start soon.
In fact, we'll make a start right now. So, welcome everyone to the final public lecture in the MAV Maths series for 2015. I reckon there have been over 40 of these public lectures delivered by Marty Ross and Burkhard Polster over the last 13 or 14 years. So, it's been an incredible contribution to my education about maths and to sharing accessible ideas about mathematics with a wider audience. You know of them because they deliver these public lectures. They're called Melbourne's Math Masters, and they wrote a series in the Age, education age, for a decade, and you'll find them, Burkhard, at least on the MAV website, presenting some ideas using YouTube, putting Rubik's Cubes inside bottles and bizarre things like that. And you'll find them on their own site, qedcat.com. But Burkhard and Marty have dedicated themselves to trying to make maths ideas accessible. And Radio National has cottoned onto this idea as well. And so today's lecture is being captured for broadcast on the Radio National Big Ideas program. So it will be an interesting experiment because we want this to be visual, but we also want it to be a lecture that works on radio. So it is really going to be quite an experiment. But you're part of it, and Marty's going to make sure that you get to get your voice on radio. Congratulations. But please welcome Marty Ross, Burkhard Polster.
Okay, thanks very much, Simon, and thank you very much to all you for coming. Not for the first time. As Simon said, kind of an experiment for us. Certainly trying to put engaging maths on the radio is an experiment. We thought engaging maths in person was an experiment. The other experiment is Burkhard and I talking together. So we've actually been talking together. These public lectures started we've been doing it for a long time, 2015, 2014, 2013, back in time, forever. And throughout all that time, starting right back, even before Simon, back into 2001, starting at Ivanhoe Grammar, and somehow convincing the MAV that having a talk on the joy of gambling was a good way to introduce mathematics to the public. And through all that time, Burkhard and I have hardly ever actually talked together. So we give our presentations, but we seldom do it together. I think the last time we did that was an MAV conference, was Theorems by Theatre. We had no idea what we were going to do, so we just destroyed a bunch of calculators, and that was the talk, and it went across really well. But we've been here for a long, long time, starting in 2001 with the joy of gambling, up to 2015. And throughout that time, we've talked about, God knows, everything we could think of, anything we thought that might capture the public's imagination. Burkhard, what's your favorite?
My favorite?
Yeah, what's your favorite?
It's always the talk that I'm giving right now.
All right, so Burkhard's favorite is today's talk. I'm not sure my favorite. Making Nick Xenophon a little uncomfortable is always pleasurable, but throughout all this, I have to say, we have to give credit to a bunch of people. And certainly the one person we have to really give credit to is Simon Pryor. That's not Simon Pryor, no, that's Zerg. But Simon, who introduced himself, has been our supporter, manager, roadie, drum supplier for 15 years and has really been an incredible amount of support, and the MAB generally, as certainly Burkhard. So the question is, what are we going to do for this talk? So Burkhard thought of the idea of yin and yang. We'll do a yin and yang talk. There's our yellow QE cat. But first of all, most of the people who come to our talks have been here before and know exactly what we're going to talk about, and of course, other people who will listen don't. So, for example, we have always in our talk 0.999 ... going on forever. What is that equal to?
1!
Wonderful. And who is in charge of maths education in Australia?
Krusty the Clown!
Wonderful. That was perfect. It was worth the 15 years just to have that. All right, okay. Now, here's a bit just to try and say, how are we going to get stuff across on radio as well as visual? So here's a ping pong rally for us to enjoy.
对的和框架是有大缺陷的，这个必须要修正。太好了，漂亮，好球啊，漂亮。漂亮，好，还有机会，
And we trust that was as exciting for the radio audience at home as it was for people here. Okay. It's obviously a tricky thing trying to present mathematical ideas at all, let alone on radio. And all I can say is we'll do our best. Okay. And we're going to do it on yin and yang. And this is where we get caught because we come up with very catchy titles, and then the question is, what on earth are we going to talk about? And so we don't know the first thing about yin and yang. So I have a Chinese source who helped me. But yin, in short, is, well, if you look it up, sort of negative and dark and cold and passive and female. And yang is positive and light and warm and active and male. And there was a recent article talking about movie reviews, and there's two great reviewers. Margaret Pomerantz was described as the yin of movie reviewing, and Stratton as the yang. Which all brings in mind a very famous speech recently, and Julia Gillard might say, I will not be lectured on mathematics by that philosophical concept. So it's very strange. My Chinese source promises me, no, yin's not the bad one. It's not the negative one. It says negative, but it's not. Nonetheless, those are the connotations that go together. But what about the yin and yang of mathematics? And Burkhard had a certain idea when he came up with the idea for this talk, and he will talk about it. But I'll try and give a general introduction to some of these ideas. And let's start with the father of mathematics, very briefly.
Let's go to ancient Greece, to the time of Pythagoras, the master egghead of them all. Pythagoras, the father of mathematics and music.
Okay, so Pythagoras, the father of mathematics and music. Here's his photo. All right, so we all know Pythagoras, okay, so kind of if you ask to name a mathematician, the one mathematician everybody can pretty much come up with is Pythagoras. Famous for the a squared plus b squared equals c squared thing. If you have a right angle triangle, so for example, 3 squared plus 4 squared equals 5 squared, 9 plus 16 is equal to 25. Don't have to be whole numbers or fractions, but we have nice whole number examples. Unfortunately, Pythagoras didn't come up with that theorem, and he didn't prove that theorem, but other than that, it's his theorem. So he did found a school, and it was a very strange school. So Pythagoras, was he the father of mathematics? Well, all right, so he thought of 3 as being male, and 4 as being female. So of course 5 was marriage. So he may have been the father of mathematics, but Daddy was a little bit of a screwball. But there was a sense in which he was the father of mathematics, and there is this sense in which you kind of have a yin and yang of mathematics, is pure mathematics and applied mathematics. And there's a sense in which Pythagoras was the first pure mathematician. So he was really trying to figure out what numbers were. So rather than just having 3 ox or 3 pyramids or 3 wise men, whatever you have, he was thinking of the number 3 and what are the properties of 3. All right? What's the properties of 4? What are numbers? How do they work? So there is some sense there. And just briefly, we're not really going to do this much, but just a bit of a sense of pure and applied mathematics. So I'll give you a couple of problems, and there'll be prizes for whoever solves it with conditions. So for example, a very typical pure question, how many ways can the letters of the word permute be arranged if the first and last places are occupied by consonants? Okay, so you've got the letters P, E, R, N, U, T, E, and you want to arrange them. How many ways can you arrange them? And I'll say just at the end, I'll offer a prize to the youngest person to solve that problem. All right, Hal, you're out of the running. Okay, so you can do it in any way you like, but the first and the last letters have to be consonants. Okay, all right. Now, a nice typical applied question. The illumination of a point on a surface varies inversely as the square of its distance from the light source and directly as the sine of the angle, blah, blah, blah. But the picture isn't hard, because you imagine you've got a wall and a floor. You've got a point on the floor you want to illuminate, and you want to illuminate with the light on the wall. And you don't want the light to be too far away, or the distance will be large, but you also don't want the point to be too low, because then the angle will be too shallow. And so the question is, how high should it be? Here the problem is said that the distance from the point to the wall is 2 meters, but it doesn't really matter what shape is that triangle. How high up the wall should you make that so that the illumination is as great as possible? And I'll offer a prize to the oldest person to solve that problem. Hal, you're in the running. Okay, I should say Hal has been to our lectures since, I don't think, has anybody been to, did anybody come to the 2001 Ivanhoe Grammar lectures? I think Hal wins the prize for our at least most enduring fan, if not our biggest fan. All right. Now, the thing about it is actually the first problem I got from the book on applied mathematics, and the second book I got from the book on pure mathematics. Actually beautiful mathematics texts from the 70s, which I've been looking at for other reasons. And it does bring out the point that, why is that first question about permuting letters applied mathematics? Why would it be there? Well, that kind of thinking, that kind of combinations and combinatorial thinking is very important for working out probability. So it's kind of the basis of what's going on in probability. Why is the second problem pure mathematics? Well, it's an application of calculus, of figuring out the nature of how calculus works. And that actually is one aspect of yin and yang, is that's what the dots are for, is that yin always has a bit of yang, and yang always has a bit of yin. So there's definitely a sense of that in mathematics, in the nature of mathematics. But we're not primarily talking about the nature of mathematics. What we want to talk about is mathematical ideas. Now, we started out with Pythagoras and the idea that 3 is male, 4 was female, and 5 was marriage. That's obviously a very crazy way of doing things, but they had another crazy way of doing things. Starting with 2, and 2, Pythagoras, and this is where we get into genuine, not crazy mathematics, is Pythagoreans had the notions of even and odd. They were sort of the first to look at even and odd numbers, to think of those as properties of numbers. 2 is the first odd number, 2 is the first even number, and they considered even numbers to be female. So does yin, by the way. I asked my Chinese source, why is female even? And the answer was, it's obvious. And if anybody has a way of telling me how it's obvious, I'd love to hear it. And then we have 3, which is the first odd number. And then 2 plus 3 is equal to 5. So, again, it's clear that 5 means marriage. It's really clear. Now, first odd number. Well, this is a little weird, of course. I apparently have forgotten 1. And 1 is the thing I've forgotten. Well, the Pythagoreans had an odd notion of 1 and an even notion of 1. There's lots of puns here. They thought of 1 as being both even and odd. And 1 has always played a rather peculiar role in the history of trying to figure out numbers. So, for example, if I ask, is 1 a prime number?
No.
So one answer, no. Hands up who thinks 1 is a prime number. About 4 hands and a couple of chickens. And how many people think that 1 is not a prime number? Okay, the majority. All right. Let me ask about Pluto. Is Pluto a planet?
It's a dog.
Okay, Pluto is a dog. Yes, all right. Okay, Pluto is not a planet. Did Pluto used to be a planet?
Yes.
Yes. Okay, and let me just say that 1 used to be a prime number in exactly the same way that Pluto used to be a planet. Okay? I'll just leave it at that. Okay? But, okay, so the Pythagoreans had the notion of even and odd, and it's a remarkably powerful notion. Just the notion of even and odd. It's kind of the simplest thing you can say about numbers, and it works out to be really well, especially if you're watching The Simpsons, which as regular attendees of our lectures know we do all the time, when our bosses think we're working. So just a quick one of Homer in 3D, one of the greatest treehouse of horrors of all time.
Ow! Watch it, Cody! Yeah. Oops. It's like, did anyone see the movie Tron?
Okay, the answer is no. Okay, so what we've got in the background there is a very famous equation, or at least a version of the equation, is rather than, as Pythagoras has, it's a squared plus b squared equals c squared, 3 squared plus 4 squared equals 5 squared, we can try to have higher powers. And so here we have, and here's a clearer view of it, is 1782 to the 12th power plus 1841 to the 12th power is equal to 1922 to the 12th power. So this is supposedly an example of a kind of like Pythagoras sum, but for higher powers, but in fact that is impossible. Fermat's last theorem says there can't be any sum. So they're having a little trickery with it, but if you looked at calculators at the time, around 1995, actually most calculators to their accuracy would say that these 3 are equal. So it was actually a very nice example. But then as people pointed out, and my guess is it was deliberate. Burkhard, do you think it was deliberate?
It was absolutely deliberate, yeah.
To make it easy.
Yeah.
And the easiness is that 1782 is an even number. Raise it to a power is still even. And so this equation reduces to even plus odd is equal to even, which is impossible. So you don't need to do a grand calculation. All you need is the notion of even and odd, and a pause on your video recorder to realize that your example doesn't work. All right. And then about 3 years later, they just decided to give it another shot, and they had another version, again to the 12th power, I think coincidentally. Burkhard might have more. And here we have an odd number to the 12th power plus an odd number to the 12th power is equal to an even number to the 12th power. So that has a shot, and actually it's a lot more accurate as well in terms of ratio. But it turns out, well, this doesn't quite work, but what you can do is think of, well, not really dividing by 3, but that's the easiest way to say it, is think of both equations dividing by 3 and comparing them. So 3,987 is the first number. That's divisible by 3, and that's easy to see. If you want to know whether a number is divisible by 3, just add the digits. 3 plus 9 plus 8 plus 7 is 15. So that first number is divisible by 3. Similarly, the second number is divisible by 3, but the third number is not. So we've got the equation, if you think of dividing by 3, ends up being 0 plus 0 is equal to 1. And so it doesn't work. And so we can actually think of it. So this is either division by 3 or divisible by 3 or not divisible by 3. Or you can think of the remainder. Okay, so we've actually got yin and yang, and we need another word. And I asked my Chinese source, what's another word other than yin and yang? And we couldn't think of anything, but we have 2 young daughters, and one of the few Chinese words I know is yaya. So, which means ducky. So you can divide things into 3 categories if you wish. Okay, so mathematics has the possibility of dividing into lots more than 2 categories, not just this or that. But simply the this or that is perhaps the most powerful notion in mathematics. Just the simple thing, this category or that category, and how do you get from one to the other. Now, there's much more I can talk about. I've got slides to do at the end on irrational thoughts. Burkhardt's going to go into some detail into permutations and the idea of even and odd. And I'll come back if there's time. Though the last time I counted, Burkhardt has 153 slides, which is a very odd number. So I'll hand it over to Burkhardt now, and then we'll see. And then we'll have some prizes at the end, definitely.
Yeah.
All right.
I think I'm down to 72. I think it's definitely going to be the heavy part of the talk. So I'll actually try to actually head it back to Marty at some point in time. Now maybe just about what Marty was talking about just a second ago. This impossibility, this impossible equations. It definitely is all due to the same writer at The Simpsons. And so when they did the first one, it was just an odd. But it didn't capture that one. So that's first equation that actually got a lot of people, posting on news groups that it's obviously impossible. And so the second equation was really meant as a response to that, and they got a lot less people kind of putting up their hands saying this is obviously not true. Right? So it's divisibility by 3 business. But it was actually meant to be a response to a lot of people saying, well, this is nonsense, can't be. Anyway, so originally the idea was actually to talk about what I'm about to talk about, and then realized, well, this is not going to work on radio at all. So I'm going to make an attempt to talk about it anyway. We'll see how we go.
Don't let reality stop you.
No, let reality not get in the way here. Let's go back. Okay. Right. So this is about yin and yang hiding in messes and permutations of things. So here I've got a couple of examples of such things. You can make up heaps more if you want to try. So there we've got a couple of animals here, 6 animals. Different height, different cuteness. Right? So we could arrange them according to various parameters. So the one that I'm going to use in a second is just going to be height, right? Not cuteness, because there will be fights over some dog lovers, some cat lovers. Height. Then we've got like a Rubik's cube here. Right? So a Rubik's cube that has been scrambled up. So that's in some sense a mess. So it's a permutation of the bits that are involved here. And then we've got something quite interesting here on the right side, which I got interested in a couple of months ago. It's mind switching. I've been practicing this with Marty and other people. So what you do is basically get a couple of people together, and then you've got a mind switching machine which you can get on eBay. And then you sit on the machine, so two people at a time, and then your minds get switched. It's really good. It's a lot of fun. I recommend it. But actually, there's a very famous episode of Futurama, which is kind of a sidekick series to The Simpsons. It's really ingenious. So this episode is about all the characters in there going for basically a mind switching orgy, and what you see there is kind of the outcome of this. Right? So you can see almost 2 images there. One is with a triangle, and one is just a straight picture. And so the one with the triangle just represents a mind, and the other one represents a body. So just for the people who are doing this on radio, just imagine a passport photo of yourself in front of you, a copy of it right next to it with a triangle on it. And so that represents you and your mind kind of occupying the same space. So everything's sorted out. And then you kind of go wild on the mind switcher, and your minds get transported to other bodies. Anyway. So whenever you've got something like this, there's some yin and yang somewhere in the background. And this yin and yang becomes very, very important within mathematics. So for all sorts of purposes. I'm just saying that these things actually in some strange way, become number-like objects, so you can actually compose permutations or masses. You can add them together, you can do all sorts of things. In some ways, it's kind of the most universal thing of, kind of the most universal concept of number you can get in mathematics. So whenever you've got something number-like, it can be translated into these masses, and you know, I'll go into a little bit more detail. And in the background of all this is still some yin and yang, giving you a lot of information about what's going on. Anyway, let's just start with maybe the simplest examples. Just these maybe 6 animals there. They sit right next to each other, so different height. We want to sort them out. We want to put them in order. The littlest one is supposed to go to the left side. Okay. So the littlest one is supposed to go on the left side. It's not on the left side at the moment. So what do? Well, we take the littlest one and just swap it with the animal that's on the left side. Okay. So we just do this. Okay. So that's in the right place. Now we're looking for the second littlest one, which is the poodle. Right? The poodle is also not in the second position, right? So we swap the poodle with which position? With the second position, right? Because that's where it's supposed to go, right? The poodle is going to swap with the guy in the second position. So there we go. Then we're looking for the third littlest one. Well, that's already in the right position. Then we're looking for the fourth littlest one. Well, that is this huge cat there. It's a huge cat. So that cat is going to now swap with the person in the fourth position. And now, basically 1, 2, 3, 4 is okay. And we still need one more swap to get it all right. We're just swapping the animals in the 5th and 6th position. Okay, so we just swap and we're done. Now, who's paid attention? How many swaps did we do? How many? Let's have a vote. Did I do 1 swap? Did I do 2 swaps? Did I do 3 swaps? Did I do 4? 4? Quite a few takers for 4. Did I do 5? Most people think 5. Did I do 6? Okay, so it's between 4 and 5. Can you just fight it out for a minute, and then we'll get back to this presentation. But actually, it was 4. Okay, so it was exactly 4 swaps. Okay, 4 swaps. Now we could actually give this. We could give this whole problem to somebody different. So that's actually the initial position here, and we could ask that person to also do some swapping and eventually kind of get back to sort it out, right, according to height. And there's like zillions of possibilities, of course. There's actually infinitely many, right? You can kind of really go crazy before you actually get settled into the position where everybody's sorted out. I'll just show you another one, okay? So here we go, 1, 2, 3, 4, 5, 6, 7, 8. 8 swaps, okay? 8 swaps. And I'll just tell you a couple more. I mean, I'm just not going to go through all of them now, right? It will take a while. We'll definitely take care of this talk.
And the next.
And Martin wouldn't have to worry about coming back with any other stuff. But anyway, so I'll just tell you a couple of other numbers that could come up here. Actually, that 4 is the best you can do. So if you want to sort out things like this particular mess here with swaps, you can't actually do better than with 4. So that strategy that I kind of proposed at the beginning, which is going for the straightforward swaps, is the best possible. This is always not the best possible. So we had like 4 swaps, here we had 8 swaps. 6 is also possible. 12 is possible. 30 is possible. 1 million is possible. 1 trillion is possible. 1 trillion and 2 is possible. What do all these numbers have in common? They're all even. They're all even. And that's actually where we get towards this yin and yang business. So whatever you try here, if you've got a mess and you've got to sort it out with swaps, it's important that you only use swaps. Whenever you have a mess and you sort it out with swaps, there's lots and lots of different ways in which you can do it, but all these different ways have one thing in common. They're either all even or all odd. So that's the yin and yang of messes. Yeah? It's the yin and yang of messes. So, and the weird thing is, like, everybody's familiar with messes, but hardly anybody's ever heard of this. Has anybody heard of this before, that there's a yin and yang of messes? So, but you've got, he's a computer scientist. He better, Should have heard something of it. Anyway, so it's as I said, nobody knows about it, but actually, I mean, mathematically, this is like one of the really, really important ones. And we'll talk a little bit about it later. So one of the reasons why this is important, you can analyze, you know, there's a lot of things you can say about things being possible or impossible whenever, you know, certain permutations come up. So for example, when you're talking about the Rubik's Cube, you can often say, people hear people saying, well, if you kind of put it together like this, then it's impossible to solve. And what's in the background of this is actually this yin and yang. So you kind of analyze Rubik's Cubes in terms of the yin and yang of the mass that's there. We'll come back to that later. Now, the thing that I thought was not possible on radio, I'm going to do now, okay? I'm going to give you a proof. I'm going to prove that yin and yang is actually what I said it is. So you have a permutation, you have a mass, and you sort it out with swaps, and it's always going to take an odd number or even number of swaps to do this. Okay? So are you ready for this? Everybody? Yes. You're ready for this? Amazing. Okay, well, if you can do this on radio, you can do nothing. There's nothing you can't do, right?
I'm convinced.
So usually what I'm about to do is in a, you know, is in an advanced book on algebra, university level, and it's not intelligible.
It's fair to say this has never been attempted before.
This has never been attempted before in the history of mankind. But I think it can actually be done. Okay, so here we go. Here we go. So whenever you've got a mass, you actually have an underlying structure. So there's actually, you know, there's masses and there's masses. So some masses are actually have quite a bit of order in them. Okay? And I want to describe to you where that order comes from. Okay, so for that one, actually, I'm going to use this mind-switching scenario. Okay? So mind-switching scenario. What's good about the mind-switching scenario is that in the kind of overall picture that I have here in front of you, you've got both the position where something's supposed to be and the bits that are kind of moved around in one picture. Right? So well, they kind of occupy the same role. Okay? So again, for the people with the radio, or maybe also for everybody else, you know, if you really want to kind of do this hardcore, you actually close your eyes now. Right? It's going to be easier if you look at my pictures. But I mean, for the radio audience, I just want to conjure up this image now, right? This is with the passport. We've got like 14 different characters. Okay, 14 different characters. Maybe think of them as your friends, right? So we're going to just put down a passport photo for every single one of them, and make a copy of that passport photo, put it right next to it, and decorate it with a triangle. Now the triangled passport photo stands for the mind. Okay. Now we're going to go wild on the mind switcher. And that leaves us with a complete mess, right? That leaves us with a complete mess. So we've got like bodies occupied by minds, but usually not the minds that belong to the bodies. Okay? So we've just got it all jumbled up. So there's like pairs of pictures that you see in front of you. There's always one straight picture and one with a triangle in it. The triangle stands for a mind. Okay? So that's a mess. That's a mess. We want to sort this out with swaps. Okay? We want to sort this out with swaps. Okay, now do you see any order in this? Do you see any order in this? Can you hear any order in this for the people who are listening to this? Probably not, okay? So probably not. But I mean, one thing you have to realize here is there's always two of one kind in this picture. So if you've got somebody's body, you know, you've also got that person's mind somewhere, right? So it's basically the same picture. The only difference here is that one of them has a triangle on it, which says it's the mind, right? Okay, so let's just go for one of those pairs. So here we've got a robot, and that robot's mind is not the robot's mind, it's that Lila's mind. Lila's mind is a person with purple hair. You know, her mind is now in the robot's body. Her mind is in the robot's body. So, I mean, yeah. Now, obviously, Lila's body is somewhere, right? Lila's body is somewhere. So we just locate it, right? Where's Lila's body? It's maybe there, okay? So we'll connect those two guys here with an arrow, okay? And then, well, Lila's body has a different mind in it. It's Kif's mind. Okay, Kif's mind. Where's Kif's body? Well, we just found it, so we also connect those two guys up. And now we're going, well, there's a mind in there that belongs to a body, so we connect those two guys up, and we just keep on going. So for everybody who's kind of lost at the moment, what we're doing is we're connecting mind to body. Okay, so we're starting with one pair, has a body and a mind. So we go from that mind to wherever the corresponding body is. Then we've got a mind here. We go from that mind to the body. We're going from mind to body, mind to body, mind to body. And obviously we've got only 14 characters that we're dealing with here. So eventually we have to get back to where we started from. In this case, that happens after 6 steps. So we've kind of cycled around here. Just from mind to body, from mind to body, from mind to body. And we've created a cycle of six of these individuals. So 6. But there's some left over, right? We've got a total of 14. We've taken care of 6. We've just put them in a cycle. And so we just start again with somebody we haven't taken care of, and we do the same thing again. Mind to body, mind to body, mind to body, mind to body, and eventually we get back to where we started from. And that, in this case, creates a cycle of 5. And then, well, there's some couples left over. So again, going mind to body, mind to body. In this case, we get 2. Okay? And then there's just one guy left over who's actually very happy because his mind is still where it belongs. But we're still going mind to body. And so, well, that's a very short cycle. Okay? So that's the underlying order of this particular mess. Okay? This is the underlying order of this particular mess. We've got a 6 cycle, we've got a 5 cycle, we've got a 2 cycle, and we've got a, what would that be? That last guy here. It's a 1 cycle, okay? And we can add it up. It's 6 plus 5 is 11 plus 2 cycle, 13 plus 1 is 14, and we're dealing with 14 people, okay? And so this sort of thing works for any mass whatsoever, right? So you've got this cycle structure underneath the mass. Okay. Now, even if you got lost, doesn't matter. Just remember, there are some things that are called cycles, and they kind of split up whatever we're talking about here. All right. Now just in case you actually want to, like, especially for the people on radio, but or maybe also for you, if you want to have another look at all this stuff in even more detail, I mean, one of the experiments I've been running for the last 6 months is I've been doing a YouTube channel on all kinds of nice mathematics. And so that's going quite well. And down here, there's actually one video on the yin and yang and the Futurama theorem. So if you want to have another look at this and maybe stop and start, check out that video. And it's, I think it's quite a nice video. And also there's other things here that you can check out. Right? So if you like these talks and you want more, right, just check out some of these videos. They come out every 1 or 2 weeks. Every 1 or 2 weeks. Okay, now keep on going. All right, now where are we actually heading? Well, we say every mass has an underlying cycle structure, an order that lies underneath it. Okay, so we've just established this. And now what we want to do is we want to head towards seeing that whatever you do with swaps, when you sort out a mess, it always takes either an even number or an odd number of things. So what we want to figure out first is, how does a swap affect this cycle structure? Okay, so here we go. Here's the cycles. There's a 6 cycle, a 5 cycle, a 2 cycle, and a 1 cycle. And now we're going to swap 2 minds. And there's 2 possibilities. Either the minds are in the same cycle, or the minds are in different cycles, right? So let's just see what happens if the minds are in different cycles and we swap them, okay? So if we have the minds in different cycles and we swap them, and I'm not going to do it, say what happened, maybe the people who are in the audience can tell us what happened. What happens when we swapped 2 minds in different cycles? What happened? We connected cycles, right? So we've got 2 minds in different cycles, we swap them, and somehow that means that the 2 cycles merge into 1 cycle. What does that mean for the number of cycles? So we started with 4 cycles, and now 2 of them merge together. So the number of cycles has gone up or down, and by how much? It's gone down by 1. And that's actually going to happen every time you do this, right? So you take two minds in disjoint, in different cycles, you swap them, and what happens is that the cycle gets merged, and what that means is that the number of cycles goes up or down? Down by 1. Okay, now guess, what happens if you take two minds in the same cycle and swap them? What do you think is going to happen? That's right, that's exactly right. Okay, so we just try this, okay? So we have two minds in the same cycle, we swap them, and what happens is that the cycle that we were in splits into two parts. And what does that mean for the number of cycles? Does it go up or down? Up. By how much? 1. Okay, and that's really all that can happen. And it's all that will ever happen. Okay, that's all that will ever happen. If you've got two minds in the same cycle, go down. Okay, so what have we got now? We've got a mess, we've got these cycles, and now we're swapping. And when we swap, as soon as we swap, the number of cycles either goes up by 1 or it goes down by 1. Okay? That's the only thing you have to remember. Okay? All still here? Yeah? All good?
Yes. Yeah.
Are you sure?
Yes.
Are you sure too? Okay. Now, next step. So we're at, our mess has 4 cycles, okay? Where do we want to go? We want to go to all people being sorted out, okay? All people being sorted out. All people being sorted out, that's 14 of them. How many cycles are in this mess here? 14, right? Somebody being sorted out means that the mind is in the body, that's a 1 cycle, right? So we're starting out with something really messy, which has 4 cycles, and we want to end up with something that's not messy at all, has everything completely sorted out, has only got 1 cycle. So we want to go from 4 to 14. 14, okay? With swaps, okay, with swaps. So how are we going to go from 4 to 14? What are we going to do? What are you going to do?
That should be the same cycle.
Yeah, that's what we're going to do. So, what we're going to go is basically going to go, as soon as we swap, we change by 1, right? We either go down to 3 or we go up to 5. Which way do you want to go? Up. Right? Okay, so we really want to go to 5, and we can actually do that, not a problem, right? And then when you're at 5, where do you want to go? Up to 6, right? And then to 7, and then to 8, right? And so the way we do this is, we're at 4 at the moment. And so what we're going to do probably is we're just going to do this swap that has the number going up, which is kind of going inside a cycle. Okay, that makes this go up. Then we're going inside a cycle again, 2 minds, that goes up to 6, and we just keep on going like this, and eventually we're going to get up to 14. Now, how many steps was that? How many steps? Went from 4 to 14, how many steps? 10, exactly. So how many swaps?
9.
Every step, 1 swap. How many swaps? 10 swaps. 10 steps, 10 swaps. Okay, 10 steps. So what have we got here? Have we got, if everything I'm saying is right, have we got an even permutation, or an even mess, or an odd mess? We've got an even mess because it's 10 steps. Do you think we can do any better than 10? No. The only way you can go up from 4 to 14 is basically up. Right? So 10 is definitely going to be the best, right? 10 is going to be the best. You can't do any better than 10. So that's all sorted. Now, can anybody see already at this stage that no matter what you do in terms of swaps, you always end up with something even? So can anybody see already why that's the case? Some people can. Some people get a kind of a vague idea of why this might be. Okay, well, let's have a look. Okay, so here we are basically. We're on a staircase. Okay, we're on a staircase that has 14 steps. We are on step 4. Okay, we're on step 4. And I want to go up to step 14. Okay, and now what we've done is basically just step up, step up, step up, step up to step 4, 5, 6, 7, 8, 9, all the way up to 14. Right? So what we could have done at some stage is actually go backwards, right? That's the only other possibility. Either go forwards, up, or you get backwards at some point in time. So for example, the first step could have been backwards down to 3, right? But eventually, if you want to go to 14, well, you have to compensate for that step backwards at some point by going forwards one, right? That's the only way you can cancel this guy out. Right? So if you want to go backwards at any stage of this process, going backwards, you have to go forwards again. So that backwards and forwards, well, that corresponds to 2. Right? This corresponds to 2. So if you only go once backwards and eventually end up at 14, well, then the total number of steps you take will be 10 plus 2 is?
11.
Right. 10 plus 2 is? 12, right? If in your process, you go back twice, okay? If you go back twice, at any stage here, you go back twice, you have to compensate for that going back by going forward twice, right? So if you go back at any stage twice, how many steps does it take to get to 14? 14 steps, right? And if you at any stage you go back 3 times, you have to compensate for that. And so it will take 16 steps, and so on. So no matter what you try here, it's always going to take an even number of steps, an even number of swaps to sort out your mess. So everybody got that?
Yes.
So that's very good, that's very good. That's good, isn't it?
Very, very good.
Okay, so you've done something now that's, as I said, has never been done in the history of mathematics and humankind. We've done a proof of the parity theorem for permutations. Well, and I think actually most of you will be able to see this, right? Okay, good. All right. Now going back to this guy here. So how is this good now? How is this good now? How does this help us with anything? So let's give you an example here, okay? Now one thing you can do with these messes is you can actually combine them, okay? You can combine them. You can do one mess on another mess. Okay, so how can we think about this? So for example, with our dogs and cats and stuff, we could say, well, let's just take whoever's in the first position here and swap it with the one in the second position. And then we take whoever's in the second position and, well, whoever's in the first position and swap it with the person in the sixth position. And whatever we get here, we call mess number 1. Okay? So this is mess number 1. So just imagine your cats and dogs sitting right next to each other in the right order. We're switching whoever's in 1 and 2, and then whoever's in 1 and 6. That gives us a certain mess. So in this case, the cute cat now is in position 2, the poodle is in position 6, and so on. Right? We could also do a second sort of mess. In this one here, maybe we go for 2 and 3 changing first, and then 3 and 4. That gives us a different mess. Now, how would you combine the two? How would you combine the two messes? Well, maybe, after I've created this one, I want to kind of put mess 1 on top. Well, what I do then is just do whatever I did before, and that gives me the combination of the second mess with the first mess. Okay? All right. Now, let me ask you, the first mess, is that an even mess or an odd mess? The first mess was swapping 1 and 2 and 2 and 3. Is that an odd or an even mess? Even mess. Second mess was swapping 2 and 3 and 3 and 4. Is that an odd mess or an even mess? Even. Okay, now we've combined them together. What sort of mess is that, odd or even? Even, why? Because odd, even plus even is even. It's even, right? So that's really like a really good insight here. When you combine messes, when you add them together, the underlying odds and evens, they also add up, right? So if you have like an even mess and an even mess, and you combine them together, you get an even mess. If you've got an even mess and an odd mess, what do you get? Odd mess. If you've got an odd mess and an odd mess, you combine them together, you get an even mess. Okay. And so you can use this sort of thing, for example, to analyze something like the Rubik's Cube. So that's one application I'm going to just talk about. Okay. So imagine a Rubik's Cube. Like, everybody's seen a Rubik's Cube? Now, Rubik's Cube consists of like these individual pieces. Let's just say you explode a Rubik's Cube. Right? You explode it, so all the pieces lie on the floor. And now you blindfold yourself and just grope around, pick up one piece at a time, and kind of put them back together until you hold something in your hand that feels like a Rubik's Cube. Okay? Feels like a Rubik's Cube. Now also it's going to be totally mixed up. And now you want to know, well, if I now just want to solve this thing by twisting and turning, can I actually do it? Okay? And now, what's the chances of actually you being able to do this if you're a Rubik's Cube master? What do you think? What's the chances? 50%. Okay? It's a bit worse than that. So guess again. What's the chances?
25.
25%. It's worse than that.
11.
11%. Let's get in here. Getting there? What do you think? 1 in 6. It's a bit worse than that. It's 1 in 12. So it's 1 in 12. So you've got a 1 in 12 chance that if you assemble the pieces of a Rubik's Cube into a cubical shape, that you'll actually be able to solve this thing in, with legal moves. Okay, and you can actually use yin and yang of masses to kind of prove this or convince yourself of this. So how does this work? Okay, so if you have a Rubik's Cube, and it's just a Rubik's Cube as it should be, as it comes out of the package. If you just take one of the faces, like one of the sides, and give it a twist, okay, then you've messed it up. It's a very, very minor mess, right? It's a very minor mess. Just like a quarter twist, right? A quarter twist from solved. That's a minor mess. You can figure out whether that's an odd mess or an even mess. It turns out to be an even mess. Okay? Okay, so that's an even mess. Now what that means is that every quarter turn, doesn't matter which way you turn it, will be an even mess. What does this imply for, say I do a million random moves. I do a million random moves with my cube, just twist them and turn them and do all kinds of other things. Will it be an even or an odd mess, you think? Why? Well, those even moves that you're doing, they're all creating even messes, right? And even messes combined together gives another, so 2 even messes combined together give an even mess, you add another even mess gives another even mess. So no matter what you do, all the possible messes of a Rubik's Cube are even messes when you kind of go with legal moves. So that's quite interesting, right? And so, have you got an idea of, you've got this really smug friend who is a Rubik's Cube master, right? So how can you really mess it up for them, right? So this guy gives you a Rubik's Cube and challenges you, just make it as hard as you possibly can, and then give it back to me and I'm going to solve it. I can solve any Rubik's Cube. What are you going to do to make it impossible for them to solve?
Make an odd mess.
You make an odd mess, exactly. How do you make an odd mess? Well, you take the Rubik's Cube, you take out 2 pieces, like 2 edge pieces, swap the positions, like you really yank them out, right? You really yank them out of the Rubik's Cube. You swap them around, push them back in, scramble the whole thing, right? Now this swapping around, that's an odd mess, right? Then the scrambling, that just adds more even stuff, so it's basically odd plus even is odd, no matter what you try it as odd. Now you give it to him, right? No matter what he's going to do there, he's just going to add more evens. He'll never be able to get out of this odd, right? Ever. Right? So these sorts of things, I mean, a lot of people know about this, right? So if you swap 2 pieces, you get into a position that can never be solved. The way you actually prove this, or you convince yourself in one go, is with these odd and even business. And actually, the whole, 1/12 that I was talking, actually, how are we going with time?
About 10 minutes, I think.
10 minutes? Okay, I'll hand back to you in a second. So get ready. Martin, are you ready?
Yep, I'm ready.
You're ready, okay.
I don't know what for what, but I'm ready.
So you're ready. So I said, if you explode a Rubik's Cube and kind of randomly put it back together again, right, you've got a 1 in 12 chance of actually being able to solve this thing, right? And 12, what are the prime factors of 12? It's 2 times 2 times 3. So you can actually account for every single one of those numbers in terms of yin and yang. So the first 2 actually really comes from what I've just been talking about. The second 2 comes from a yin and yang that you can see when you kind of, instead of focusing on the pieces kind of being shuffled around, actually on the individual stickers on the edge piece. Remember, an edge piece has kind of 2 stickers on it. So that's kind of a 2 thing. And then there's the 3. The 3 comes from another, it's actually one of those yin, yang, and yaya things. that goes with the corners. So the corners, every corner on a cube has like 3 stickers on it, and so you can kind of twist them in 3 different ways. There's the yin, yang, and ya, and so you can actually really make sense of this 1/12 missing, and yeah, it's actually really, really nice things. Lots of other things can be analyzed. This is like within mathematics. As I said, these permutations, they turn kind of into numbers. Everything in mathematics that looks like a number can be turned into permutations. So it becomes very important, but I think it's enough for today. It was quite challenging, I think, challenging for me. But as I said, you've done something today that's not been done before, so you can tap yourself on the shoulder, and I hand back to Marty.
Okay, thank you. Okay, so he's handed me back, and the question is, what should we do with our remaining time? Maybe we should do the puzzles. So we had 2 puzzles. One
But
was
that's that much time, right? It's 1:24, right?
124. So yeah,
But 5 minutes.
yeah, I know, but we'll see if we've got some answers to the puzzles. So the first puzzle, if I can bring it up. We don't want that. That's the end, but.
It's a good end anyway.
Yeah, okay. So, how many ways can you permute the letters of the word commute? Be arranged in the first and last places. The first and last places occupied by consonants. And we need the youngest person with an answer. So who thinks they have an answer to this? All right, Robert is not the youngest person. Wendy
Okay,
is not
I'm
the
just going to go
youngest person.
around and they have to whisper it in my ear, right?
Okay. Okay. And Mr. Lego, how old are you?
Okay.
15. Do we have anybody younger than 15? Mr. Green? 8. Do we have anybody younger than 8? Okay.
What am I doing?
That's fine. So we have the youngest person. And what do you think the answer is?
What was the question?
That'll get a prize anyway. The question, do you have an answer?
Yeah,
thousands. Thousands. We will continue. Okay, do we have any, so Mr. Lego's 15. Do we have anybody younger than 15? Yes? How old are you?
Okay.
You're also 8. Oh, you could have gone first. Okay, and what is your answer? 2. Bit bigger than 2. Anybody else younger than 15? Yes?
16.
So, Mr. Lego, you're 15? Okay. So, and I've got a pretty good idea you're going to have the answer. What's your answer?
1,440.
We will continue. Okay. What answer do you have?
16.
16. Okay. It's open. Yes?
Me?
Yes. Are you older than 15?
Yeah, nearly 49.
Nearly 49. 49 is bigger than 15.
Anyone else?
Yes. Okay. Robert,
Well, I have the same answer.
1440?
27.
Oh, wait.
Yeah.
Wendy, how old are you first? Sorry, roughly?
29.
Okay. Anybody younger than, anybody in their 20s? Okay, Wendy.
720.
720, and Wendy wins the prize. Okay, big round of applause for Wendy. Okay. Okay. So, we've got, here are letters, okay, and we've got 4 consonants. So how many choices do we have for the first spot?
4.
4 choices. How many choices for the last spot?
3.
3, because we've used one of the consonants. Now, here's the problem. How many choices do we have for the next spot? 5. What about the 2 E's?
5 factorial on 2.
The fact that, what we'll do is, let's color, we've all in red, let's make the E's look different. And then we definitely have 5 choices. And 4 choices, and 3 choices, and 2 choices, and 1 choice. And that product, multiply them all together, and that gives you 1,440 choices, but the e's are actually the same, so each of those permutations corresponds to just 2 permutations correspond to just 1, and so the total is 720 permutations. Okay, very good example of, I guess, applied mathematics. Okay, and very quickly, we won't go to the answer.